Okay, in the last lecture, we wrote down Feynman momentum space Feynman rules for Green's functions. Okay, these ones, and which you can use to write down expressions for Feynman diagrams using those rules. Another object that will be of interest to us will be the Fourier transform of this object, and today we want to write down the Feynman rules corresponding to the Fourier transform of this. So, let me first define the Fourier transform of this object. So, this is a function of n variables x1 to xn. So, I define Fourier transform g tilde of p1 to pn by Fourier transforming each of the variables. So, here you have d4x I, let me d4x1 to d4xn, okay, then e to the minus I p1 x1, okay, and then for the x2 variable I will have e to the minus I p2 x2, which I can put here, and so forth for all the terms up to xn. And then of course, we should have here g okay, that is the Fourier transform, and we will see later that g tilde is an object of interest, and we want to, that is why I write down the Feynman rules for this. Okay, so this will be simple because we already know how to write down an expression for gn, okay, and all we have introduced is this exponential factor, and there is an integral over the xi's. Now recall that the dependence on xi of gn was quite simple. Okay, the dependence of this on xi's was like this. So, xi dependence was merely e to the minus I li xi if li enters the external point. Okay. So, li is the momentum that enters into the external point xi. Then you put e to the minus I li xi, and if li exits, then you put e to the plus I li xi. Okay, that is what we had. And now this is why it is very simple to handle the x1, because g depends on xi only through this factor. This is the only place where xi appears, right? Now, if this is the only place, let us look at x1. So, x1 is the x1 appears only through this exponential factor in g, and this is the other place where you have x1. So, you can combine these two exponentials and you can do the integral over x1. Okay. So, these two exponentials will combine, and when you integrate over x1, you will get a delta function. Okay. So, handling x1 will be simple. So, going to the Fourier space from x to p, that will be quite easy. Okay. So, that is what we are going to do. It will be better to have an explicit example where I can show these calculations rather than talking in general. So, let us go back to our same diagram which we have been looking so far, which is this one, this diagram, and look at it in the Fourier space. Okay, so let us see. So, here I am, so right now I am drawing gn, this diagram which I was calling f. So, you have this object and we had assigned the momenta like this last time. So let's do it again the same way, but you can assign it differently if you wish. And this was k5, which was assigned this way, and this was k6, which was going this way. Okay, and we have already done the integrals over the vertices, so they are not there anymore. They left behind the delta functions, momentum and momentum conserving delta functions at the vertices. Okay, anyhow, so let's look at this. So this we had called as f of x1, x2, x3, x4, and now we want to have f tilde of p1, p2, p3 and p4, and this will be exactly this factor. So I should write it down, d4xi and e to the minus I pi xi. So I have written for ith one this piece and this piece, and of course I have to multiply this 4 times. I mean multiply these 4 factors. Okay, so now I've taken care of these parts. Now I should only write gn, or rather f of this, which you recall was the following. So for each propagator I had an integral corresponding to the momentum that runs through that propagator. So we had d4 k1 over 2 pi to the 4 up to d4 k6. We have 6 propagators, and for each one we have to have an integral. And recall what the piece was corresponding to the external points. It was just simply this. Okay, so we include all the factors corresponding to the external points, and you get e to the I k1 x1 up to e to the I k4 x4. Okay, there are only 4 external points. So you have this, and then I should have all the 6 propagators, which I will split into 2 when I am writing 2 parts. So you have k1 square minus m square plus I epsilon I over k4 square minus m square plus I epsilon. So that's 1, and the remaining 2 are I over k5 square minus m square plus I epsilon and I over k6 square minus m square plus I epsilon. So I have taken care of all the propagators, and then we remember that we had delta functions 2 pi 4 times the delta functions at each vertex. Okay, and you have to see that the momentum conservation holds there. So k1 plus k2 enters and k5 plus k6 exits. So the sum of all the momenta entering should be 0, which is k1 plus k2 minus k5 minus k6. So the sum of all momenta entering is 0, and you had another one k3. So this was 3 plus k4 plus k5 plus k6. Okay, and then the other factors of minus I lambda over 4 factorial squared times 1 over 2 factorial times the combinatoric factor. Okay, so let's do the integral over x1, x2, x3 and x4 for the reasons I was talking above. So let's say when I am doing the integral over x1, I take this piece, I take this piece, and I integrate over x1. I get a 2 pi 4 delta 4 k1 minus p1. Okay, so let me write here integral d4x Let me try to change the color. Okay, so if I do the integral d4, okay, this might not be good. d4xi e to the, where is it, e to the minus I pi minus ki. Okay, this will give 2 pi to the 4 delta 4 pi minus ki. Okay, which will, when you integrate over the ki, because you have these k integrals. Okay, in fact, I should have split this also into two factors like this, which is fine, doesn't matter. So anyway, when you do the integral over k1, k2, k3 and k4, the k1 will get the k1 will be forced to become p1 because of this delta function everywhere in this expression. K2 will be forced to become p2 everywhere in the expression, and so forth. Okay, so let's do that. So this will be gone, this will be gone, and these four factors will be gone. Okay, and they will leave behind these 2 pi 4 delta 4s. Okay, and I will also do one more integral now. I will do 4 integrals, so d4 k1 up to d4 k4 by over 2 pi to the 4, and these 2 will remain, k5 over 2 pi to the 4. Okay, so we'll do up to these 4, and when I do these 4 integrals, I will be just setting k1 equal to p1, k2 equal to p2, and so forth, and these 2 pi 4s will cancel against these denominators. Okay, so 2 pi 4s will also go away. So the answer will be this. I should start writing d4 k5 and d4 k6. Okay, so what we get is d4 k5 over 2 pi to the 4, d4 k6 over 2 pi to the 4. Let's go back. We have these 4 sitting here, and these 4, there is no integral over k1, sorry, yeah. So when I'm doing this integral, this will be set, k1 will be set to p1. Okay, let me go back again. So I have 4 factors, and they will be I over p1 square minus m square plus I epsilon up to p4 square minus m square plus I epsilon. Okay, now these do not depend on these integrals, these variables k5 and k6. In fact, they do not depend on any other variables because these are the externally specified momenta. So I could have just written it like this. I could have written it outside the integral. So maybe I should do that. Okay, I think I cannot. So let's okay, so let's leave it. So I have I over pi square minus m square plus I epsilon, and we have all the 4, so that's the product. Then you have integral d4 k5 over 2 pi to the 4, integral d4 k6 over 2 pi to the 4th, and then what else we have? We have these 2 propagators. So I write I over k5 square minus m square plus I epsilon, I over k6 square minus m square plus I epsilon. That is fine, these 2 are gone. and then we have these Dirac delta functions, okay, and all these factors. Now what I'll do is I'll do a K5 integral, or rather a K6 integral. Let's see which one I was doing in my note. Okay, I will do a K6 integral now, okay, and that is easy because I can use up this delta function. So the 2 pi 4 in the denominator here, that will cancel against this 2 pi 4, so that goes away. And when I do integral d4 K6 of this delta, it will set K6 equal to K1 plus K2 minus K5, right, at all the places where it appears. So let me do that. So I will change this one now because I am doing that integral. Okay, that doesn't work. So this one will be changed to I over, what was that, K1 plus K2 minus K5. K1 plus K2 minus K5 whole squared minus m square plus I epsilon. Okay, I have just done the K6 integral, and here you had a K6 squared, which I have changed to this. Okay, let's see what more. So this I have taken care of, this one is taken care of. This integral I have done, this factor of 2 pi 4 is taken care of because it cancels against this one. So now what I have is 2 pi to the 4 times delta 4 K3 plus K4, and here for K6 I should write K1 plus K2 minus K5. So let's see, K3, I am writing the argument of delta 4 here, K3 plus K4 plus K5, and for K6 I should write K1 plus K2 minus K5, and this cancels, which is just there is something going wrong. And what is going wrong? Yes, I know. That is fine. Let me just write it. I have made a slight mistake. Okay, this is what you'll get. What I forgot is that when I did the integral over K1 up to K4, these delta functions, their arguments will also change, right? So this K1 will become P1 and K2 will become P2. Okay, because that's what we are doing here. So instead of this, actually I will get P1 plus P2 plus P3 plus P4. Okay, so here it's fine. The way it is written is fine, but at the next step, actually everything is fine. So since I'm writing just now, it's all okay. There's nothing wrong. So I get 2 pi to the 4 delta 4 P1 plus P2 plus P3 plus P4. Okay, so this is also taken care of, and then you have these last factors. Let me write square times 1 over 2 factorial times combinatoric factor. Okay, that's, yeah, I have done the integral over K6, so I should not have it here, right? I have used up the delta function, this one, to do the integral, or rather this one I did use to do the integral, and this is the one which remains. Okay, so this is good. Now I will do a slight change of notation. Instead of using K5, I will use Q. Okay, and what else? Yeah, here also there is a mistake because now K1 should become P1, right? Because we had an integral, delta function integral, which had forced the P1, P2, K1, K2, K3, K4 to P1, P2, P3, P4. Now this is fine. So you see there is only one momentum over which we still need to do an integral, and that is k5. All other are completely fixed because they are fixed by the specification of g. See, g tilde has this p1 up to p4 in our expression. So they are given externally, they are specified to you. Okay, and what is left is only one integral over the dummy variable k5, which we are going to call as q now. Okay, so what we have here is now the following. So let me go back to this diagram, and k5 now I am calling as q. Okay, so one momentum here, and you see that the final result is the following. So I'll just, in the next slide I'll write k5 as q. Okay, so the final result is this for Fourier transform of this, which was integral so we have one q here which is going like this, which was being called k5. Okay, and all the external momentum they have been fixed. The momentum which was flowing in here has been fixed to p1 and p2 and p3 and p4. Let me go back. So when we did this integral, we set k1 equal to p1, right? So I can draw the same diagram with p1 here, because p1 has k1 which was flowing like this here has been set to p2, and the k2 which was flowing like this has been set to p2, and k3 and k4 have been set to p3 and p4. Okay, and remember what happened to this one, this, because you have momentum conservation, everything else is fixed. So this one has momentum. What momentum is running here? It is p1 plus p2 is entering into the vortex, but q leaves out, so whatever left is here. So you have p1 plus p2 coming in minus q leaving out. Okay, so this is what goes in here, and that's why you have this thing p1 plus p2 minus q. Its k5 has become q. Okay, so you see that all the momenta in this diagram, all the momenta on the propagators have been completely fixed except for one, the q, over which you still have an integral, and the result is the following. So let me write this as f tilde p1 to p4. Okay, so this is not now f of x1 to x4, this is f tilde p1 to p4. Okay, so I am specifying the external momenta here now based on what the calculation that we did, and the result is this. First factor was for each external propagator I have such a piece, and by external propagator I mean the propagator that connects to the external points. So you have I over p1 square minus m square plus I epsilon. Okay, for this one you have p2 square minus m square plus I epsilon, p3 square minus m square plus I epsilon. Okay, so you see that these external lines have nicely factored out of all other things. Then what do we have? Then we have d4q over 2 pi to the 4, that's here. Okay, and then I have these two propagators. Okay, this one and that one. Let me write that down. So this is the one which earlier we called k5, and this has become now I over q square minus m square plus I epsilon, and then this one has become I over p1 plus p2 minus q square minus m square plus I epsilon. Okay, then what else? you had a minus I lambda over 4 factorial from each vertex, 1 over 2 factorial from the exponential, and then the combinatoric factor. I think that this is all correct. Not yet. There is one piece which is missing, which is this piece, times 2 pi to the 4 delta 4 P1 plus P2 plus P3 plus P4. You see, this one is overall energy momentum conserving delta function. So it says that the sum of all momenta, 4 momenta, P1, P2, P3 and P4 entering into the diagram is 0, which just means whatever enters should exit. Okay. So because right now in the diagram we have everything entering, the sum should be 0. If I had drawn the P3 and P4 lines going out, if I had arranged it that way, then you would have gotten P1 plus P2 minus P3 minus P4. That would mean P1 plus P2 is equal to P3 plus P4. But because everything is ingoing right now in this diagram, you have the sum of all momenta entering to be 0. Okay, so that is the expression for the diagram which we have. Okay, and this is really the diagram in the Fourier space. Okay, so what we see that is that in this case you have only one momentum left unintegrated, and that is called loop momentum. So Q is called the loop momentum. Okay, and Q runs, of course, from all the components run from minus infinity to plus infinity. Okay, and this diagram has only one unintegrated, only one loop momentum, because this is a one loop diagram. So there is only one loop here, and that is why when we did this computation we got only one variable Q, which was still remaining and which needs integration. But if you are looking at a diagram which was having more than one loops, so let's say a 2 loop, for example, if you look at a 2-point function, okay, like this. So this one, if you had only this, if you do the same exercise as I have done here for this 4-point function, if you were to repeat the exercise for this, which I would encourage you to do, okay, and do the same steps, you will see you are still again going to be left with one loop momentum Q. Okay, so you will be left with one integral. But if you start doing this one, you will be left with 2, Q1 and Q2, because that's a 2 loop. So for each loop you will have one loop momentum which you will need to integrate over. Okay, good. Then so what we can do is make the Feynman rules for calculating F tildes or G tildes. Okay, so when we are looking at these Green's functions in Fourier space, the Feynman rules are the following. So again you assign a directed momentum to each propagator okay, and for each external propagator you have to write down this. Okay, these 4 pieces. So we have 4, so we should include this piece for all the 4. Okay, then we should include 2 pi 4 times an overall energy momentum conserving delta function. Okay, and then include d4qi over 2 pi to the 4 for each undetermined loop integral, for each loop. Okay. By undetermined, I mean the following. In the case of one loop, you see we had these two internal lines, two internal propagators as opposed to 4 external propagators, and you saw that the momentum flowing in this line got completely fixed in terms of the external momenta and this loop momenta. So you do not have any freedom left for this one. So in general, what will happen is certain propagators will have their momenta completely fixed in terms of all others. Okay, so if you are looking at two loop, you will have two undetermined momenta q1 and q2, and all other propagators will have completely fixed values of the momentum that flows in there, okay, in terms of external momenta and the loop momenta. Okay, so this is what we should do, and then assign momenta to all the internal propagators using momentum conservation. Let me explain. So here you see it's one loop, so these lines momentum is fixed p1, p2, p3, p4 because they are given to you. This one you say it's q, and this one you write down by using the momentum conservation. Okay, p1 plus p2 minus q flows in here. Okay, and that's what I am writing as a rule, that you should assign momenta to all internal propagators using momentum conservation, and of course some of them will remain free, just like the one which is q. Okay, and then of course include minus I lambda over 4 factorial power v if you have v vertices, 1 over v factorial if you have v vertices, and then multiply the combinatoric factor. Okay, so this is all I wanted to say about the Feynman rules for this Fourier transformed Green's functions, and I would encourage you to play around with some other diagrams. For example, you can try to write down the expression for this one. So you are looking at Green's function, or let's say Feynman diagram with p1, p2, p3, p4, and where p1 is this, p2 is this, p3 is this, and p4 is that. Okay, now try to assign first the momentum here and see how many are undetermined. Okay, and then fix all the remaining ones in terms of the external momenta and the undetermined momenta, and write down all write down the expression using these rules, okay, which you have made. And in case you are feeling unsure about how to write or what it means, you go back further and you start from here. You start from here. So you write the Gn in terms of position space, and then introduce this Fourier transform, and then follow the steps. Okay, and then eventually you will end up at the answer. Okay, either way, whichever way you prefer. Okay, so we'll meet in the next video.